Now, the last type of function that we want to look at is a logarithmic function. And I suppose in its most basic essence, a logarithmic function is the inverse to an exponential function. Okay, exponential functions, over time, they kind of grow rapidly over a short amount of time, whereas the logarithmic functions, they seem to level off. Their growth gets less and less and less over time. Okay, so the biggest difference between them is that an exponential function gives rise to huge growth over time, whereas a logarithmic function gives rise to very, very slow down or stunted growth over time. If I was just to draw them very quickly, we would say that a logarithmic function looks something like this. So it starts off and is growing quite rapidly, then it kind of tailors off. Okay, whereas an exponential function is something like that. Now, if I draw a line between them, you get what's called symmetry. So in other words, they are related to one another through symmetry. Now, if it's a case that these two are symmetrical about the line y equals x, well then we know from functions that graphs that are symmetrical around the line y equals x are what we call inverse functions of one another. And we'll deal more about inverse functions later on. But that is how we know when two functions are inverses of one another. Okay. So first and foremost, logs are the inverse function to exponential functions. All right, and there's that symmetry I was talking about. Now you've got three lines here. First of all, that's the line y equals x. Okay, so that's the mirror, so to speak. There are two other functions, red and green. You should know at this stage, obviously, that the red one is the exponential one, because over time the growth starts to accelerate. Do you see that? So the growth is accelerating, and then it becomes very, very big growth the further along the x-axis we go. So that is your exponential function. Here we notice that the growth is decelerating, that there's not as much growth going on the further along the x-axis we go, and that's your logarithmic function. So the one thing I do want to say here is that functions that are inverse to one another are always beautifully symmetrical around the line y equals x. And that's in fact what we're going to finish this chapter with sometime next week. It'll be the last thing we'll do in terms of functions. Notice, as we said already, the symmetry of 3 to the x and log to the base 3 of x. So therefore this one is 3 to the x, and this one is log to the base 3 of x. Now, two things I want to point out here. First of all, every exponential function has a base number. All right. If you remember when we were dealing with indices, you have the base 3 and the index x. Okay, so that's a base 3 indice. Now, if I take log to the base 3, notice what I'm saying. It has exactly the same base. So you've got 3 to the power of x and log to the base 3. These two are inverses of one another. So when the base in both the exponential function and the logarithmic function match, then they are inverses of one another. Okay, and what I want to demonstrate here mathematically is how that actually works out when we use these things to calculate. So you have 3 to the power of x and you have log to the base 3 of x. Now here's what I'm going to do. I'm going to put the logarithmic function into the index. All right, so you get 3 to log to the base 3 of x. So I'm taking this and putting it in as the power to the base 3. Notice that the base of the index is 3 and that the base of the log is 3. If you do that and both bases match, the answer is simply x. And likewise, if I take this 3 to the power of x and put it in here, I'm going to get log to the base 3 of 3 to the power of x. And again, the base of the log is 3, the base of this particular index form is 3, so therefore they will cancel, leaving the answer with x. And that's what inverse functions do. They basically meet and they neutralize one another because they're doing the opposite thing. Okay, more about that later, but it's just a nice little curiosity in terms of how we can use logs and exponential functions in order to simplify an awful lot of mathematics that we'll be dealing with later on. This feature of all inverse functions we will deal with when we get to the end of this chapter. So we'll be dealing with inverse functions at the very, very end. Now, if they're inverse and their job basically is to undo one another if they have the same base, therefore we can get something like this. So look at this one. Log to the base 5 of 5 to the power of 3. Now just take them separately. What's the base of the log? The base of the log is 5. What's the base of that particular index form? The answer is 5. So once the bases match, you'd work them out, cancel them, and the answer is 3. And the same thing goes over here. If you take this index, the base of this index here is 6, and the base of this log is 6. So therefore, if the base of the index form is 6 and the base of the log is 6, then it leaves you simply with the power, which is 8. So what they do when they're used together is they simplify an awful lot of mathematics that we will be doing when we're looking at exponential functions later on, in terms of using them for calculations in differentiation and integration and so on. When the bases match, the functions cancel. We've had that already. And graphing them is one of the first things we're going to be asked to do. Very simple. You take your calculator, you put in your logarithmic function, and you generate your table. Logarithmic functions also are transformed in the same way as other functions. Now, what does that mean? Again, let me do some examples. I think it's much easier when you see the examples in play. So this is page 153, question 1, part 2. Graph the log to the base 5 of x, where x is an element of real numbers, and it's between 0 and 125. Now, the one thing I want you to notice here, just take a look at your domain values. Your domain values are going between 0 and 125, okay? But 0 is not allowed to be included. Look at the symbol. In fact, you can never get the log of 0. The log of 0, if you tap it into your calculator, log to the base 5 of 0, you're going to get a syntax error. It doesn't work, okay? So you can never have 0 as the first value of a domain for a logarithmic function. Just keep that in mind. So the highest value is 125. So what are we going to do in our calculators? Well, the first thing we're going to do is put in the function, log to the base 5 of x. So you go to mode 3 for your table. F of x comes up on your screen if you can see it there. And you put in this button. You see the button that is just underneath, if I can hold it there, the button that's just underneath the power button. Yeah, that's log to the base of a number. Now, if you press that, you'll get what it says up there. Log to the base and with a number, spaces that you can fill in yourself. Okay, so I'm going to put in here log to the base 5 of alpha x, because don't forget alpha x is the spot into which your domain values are going to be fed. Okay, so log to the base 5 of x. Now, I can't start at 0, so I'm going to start at 1. And then I'm going to move up along in spaces of certain numbers. Okay, so I can do that. I can start, or I could, if I wanted to start at 0, I'm going to get an error anyway, and I could move up in steps of whatever. But I'm not going to generate 125 values. I'm going to move up in steps of maybe 25, okay, and see what that gives. Now, when I do that on the calculator, because I've already done it here, you're going to get something like the following. There's the function that should appear on the screen of your calculator. And when you put in 1 up to 125, probably in steps as I've done here of 25, well then, notice the points that I can plot easily. That's easily plottable, this one, and this one. But look at what I've done in terms of the values of x. I have taken them in steps of 25, okay? Now, one thing I want to say to you here, the 0.10 will always be the first point of a log that is written in its most basic form. So log to the base of x. 1, if you put a 1 in here for x, that will always give you 0 as the answer, okay? So you can include 10 if you have a basic log as your first input-output values. If not, go to 5, go in steps of 25 and get the values along the y, output values, and then simply plot the ones that are easily plottable. So you'll get something like this. Whoopsie-daisy. You'll get something like this. Okay. Now, you get your 0, 1, which is there. Then you have, something wrong with my computer today, then you have 5, 1. So 5, 1 is there. And then you have 25, 2, which is here. And finally, the only other one I want to look at is 125, 3, which is there. Now, there's enough information there for me to be able to draw this. I don't have to draw these 3 here because they're difficult enough to plot. So if I plot 1, 0, 5, 1, 25, 2, and 125, 3, then all I've got to do is join them. And you'll get exactly the same as what's on that graph. Okay, so generate the values as you wish, but usually only plot the ones that are easy to plot. Now, you can put these in quite easily now. 50, well, there's that point there. Then you've got your 75, that's that one there. And then you've got your 100, which is that point there. So you can put those points in after you've drawn the graph. A little bit of a cheeky way to do it, but you can do it nonetheless. Okay. Okay, next question. Worked example, page 153, question 5. The graph of g of x, which is log to the base 2 of x, is shown. Now, notice I've done this color-coded. So g to the x equals log to the base 2 of x. That is in blue. So therefore, it's that function here. See that one? That's the function we're dealing with. So let me write that in. That's log to the base 2 of x. Match the functions mentioned below with those that are graphed. Now, I've got 3 functions here, and I've got 3 functions remaining to be labeled. So let's see if we can work these out. First of all, let's take this one. What does a coefficient do to any function? A coefficient stretches, okay? It stretches your vertical height. That's exactly what it does. However, what you can also say is this. It triples the y outputs. Now, that's another way to look at it. So if you take the blue line here as being the original log to the base 2 of x, okay? Just take a value along that line that's easy to read. Let's take this one here. See that value? Okay, that's above 2, and it has a value of 1. So that's an easy value to read. Now, if I multiply that by 3, it's going to shoot up to 3, which is there. All right, straight away it's on the green line. But let's just verify that and see. Let's take another one that's easy to read. Let's take this one here, 4, 2. Now, if I take that height of 2 and I multiply it by 3, it goes to a height of 6. So it's definitely the green line. So the green line is 3 log to the base 2 of x, because it's 3 times higher in terms of the outputs than the original function. Okay, so that's that one taken care of. Next one, log to the base 2 of x minus 3. Now again, remember what I told you? When x is directly affected by a number, take it out. X minus 3. Set it equal to 0. X equals plus 3. Which means that this one is the same as the original blue function, but it has been pushed 3 units to the right hand side. So therefore, take the blue line, take that point there, and push it 3 units over to here. So therefore, that purple line is log to the base 2 of x minus 3. Now I know by process of elimination, we can easily say, and the last one is a black line. But let's just show where I'm going to get that from, okay? Log to the base 2 of x, you notice that? That there is the original function. That's the blue line. What have I done? I have taken the blue line and I've pushed it up 4 spaces. That's what happens when you add on a constant. So you're taking that and you're simply just lifting it up 4 units. So that means this point here on the blue line, which is 0, will go to 4. See that? This point here, which is 1 on the y-axis, that will go to 5. And then this point here, which is 2 on the y-axis, will go to 6. So the last one then is this black one, which is log to the base 2 of x plus 4. Now, the one thing people might be confused on is this one and the last one. When you put a coefficient in front, okay, it's the outputs only that are multiplied by 3. They still have the main values, but the outputs are multiplied by 3. So if I'm going to just do that again, and I'm going to do it very quickly because I just need to make sure you understand this. Let's take the first one, all right? We know that the blue line there is log to the base 2 of x. Okay, now let's take the first one. 3 times log to the base 2 of x. So therefore, you start to the blue line, and the outputs are multiplied by 3. So what I mean by that is this output here, which is 0, is multiplied by 3. It stays 0. This output here, which is 1, is multiplied by 3 and therefore goes to 3. See that? This output here, which is 2, is multiplied by 3 and goes to 6. And they fall perfectly onto the green line. Whereas, when you're dealing with the other one, let me just take those points off there. And take those off. Give me a bit of space. Okay, when you're dealing with the last one, you're dealing with this one here, you're taking the function, the blue line, but you're pushing the whole thing up by 4 units. So this one here gets pushed up by 4 units to there. This point here gets pushed up by 4 units to there. And this one here gets pushed up by 4 units to there. So you're basically simply shoving the original blue line up 4 spaces along the y-axis. And that's the difference between the two of those. Okay. Worked example page 154, question 9. This is the second last example. One more, and then I'm going to give you some to do. The graph of the function y equals 3 log to the base 6x is shifted 3 units downwards and 3 units to the right. What is its new functional form? So y equals 3 log to the base 6 of x. Okay, it shifted 3 units downwards. So that's down 3 units. That means if you're decreasing, you're subtracting 3 from this function. So you've got to put your minus 3 at the end. Okay, and the last thing we want to do is to move it 3 units to the right. Okay, so x equals plus 3. But what does that mean? If you bring the plus 3 back over here, x minus 3. So what was the x has to be turned into minus 3. And that is the new functional form. All right, do it again very quickly. So we have y equals 3 log to the base 6 of x as the original form. 3 units downwards, that's easy. If it's a vertical shift up or down, it's just a constant. It's going down 3 spaces. So I put a minus 3 at the end. If we're moving horizontally, we directly affect the x. So 3 units to the right, what does that mean? That means x is equal to plus 3. Okay, if you're moving to the right, it's x equals plus 3. Now, join these two. Bring the plus 3 back over here. And that means that that is the form of x in brackets that has to be used. And that's the new functional form. Okay, and finally then, a question like this, which is quite easy. For each function below, identify the largest domain for which the function is defined, and hence identify the corresponding range. Now, when we're dealing with the domain, we are dealing with x values. Okay, x values. So what I need to do is I need to remember this. You cannot get the log of 0. See that? So log to the base 2 of x plus 1 minus 2. You cannot get the log of 0. So this part here simply cannot be 0. Now I want you to think for a moment. What number, if I was to put it in for x, would turn that bracket to 0? So x cannot be 0, so therefore, sorry, the x plus 1, I should say. X plus 1 cannot be 0, so therefore x cannot be equal to minus 1. Meaning that x can only be greater than minus 1. Now, any value after minus 1 to your heart's content, but not minus 1. So as far as your domain is concerned, the largest domain for which the function is defined are all x values greater than minus 1. Now, what about the corresponding range? Well, keep in mind that the domain is the horizontal value. We've already sorted that out. That can only go from values greater than minus 1. But what about the horizontal, the vertical, up and down? Graphs go up and down forever. The graph keeps on going upwards and it comes from a very, very deep position downwards. So there is no limit. So on your range, there is no max and there is no min. Very easy. No max, and there never is, and no min. And that's all you've got to say. All right. So again, all you've got to do is remember that the algebraic part after the log cannot be 0. So you ask yourself a question. What number would I put in for x that would turn it to 0? What value of x can it not be? So x plus 1 cannot be equal to 0, meaning x cannot be equal to minus 1. See the algebra in there? So therefore, if it can't be equal to minus 1, what values does it have? Therefore, x must be greater than minus 1. And that's your domain. And then your range will not have a maximum or a minimum. That's all they want you to do with exponential functions. So I'm going to leave you with these, page 153 and 154. The examples that I have done previously just there are exactly the same type of questions that you're being asked here. So you get these done very, very quickly. And on Monday we'll have a live class and we're going to go through all the different functions that we've dealt with over the last couple of days. We've done the linears and the quadratics. I now want to look at the cubics. I want to look at the exponentials. I want to look at the logarithms.